In furthering our ability to integrate various functions, we now have to consider a different style of function along with a new technique in order to integrate it. Trigonometric substitution is a technique that is specifically used to integrate functions that include, as part of the integrand, an expression of the form the square root of a squared minus u squared, or perhaps the square root of u squared minus a squared, or even perhaps the square root of a squared plus u squared, where a, in any of these situations, a is a constant and u is a variable expression. You may notice that each of these is something that can be the result of the Pythagorean theorem applied to variations of a right triangle. So we will consider each of these scenarios one at a time, along with an example that uses each. To start with, we will look at triangles that would produce this expression as the length of one of the sides. For a square root of a squared minus u squared, we would be looking at a right triangle drawn with the angle in question in standard position, which we will label theta. In order to produce an a squared minus u squared, a must be the length of the hypotenuse, and u must be the length of one of the two legs. It can be done with either, but by convention, in a situation such as this, u is considered to be the length of the opposite side of angle theta. In this way, the length of the adjacent side can be determined by solving the Pythagorean theorem using u for the length of the opposite side and a for the length of the hypotenuse, where we would start by subtracting u squared from both sides and then taking the square root of both sides, thus producing the square root of a squared minus u squared. And that would be the length of the adjacent side. This will allow us to rewrite the expression, the square root of a squared minus u squared, in terms of the measure of angle theta. In this case, we would use the substitution beginning with the expression that sine of theta is equal to u over a. So we're going to use a trigonometric function that relates the other two sides of the triangle, not the one with the radical. Multiplying both sides by a gives us a sine theta is equal to u. And we can now use this as a substitution in the integral. Let's look at an example to start. Consider the integral of 1 over x squared times the square root of 9 minus x squared dx. The radical, the expression under the radical, is of the form a squared minus u squared, where a is 3 squared and u is x squared. Using the triangle, as we described on the previous page here, 3 would be the length of the hypotenuse, and x would be the length of the opposite side of angle theta. And by the Pythagorean theorem, the radical expression 3 squared minus x squared, or 9 minus x squared under the radical, would be the length of the adjacent side. This would allow us to use sine theta is equal to x over 3, or 3 sine theta is equal to x. This will allow us in the integrand to replace all instances of x with 3 sine theta. Now, of course, with substitution, we would also need to replace the dx. We can do so by differentiating 3 sine theta equals x on both sides with respect to x. That would give us 3 cosine theta d theta is equal to dx. So we can swap out our dx for 3 cosine theta d theta. From here, we can clean everything up. So in the numerator, we have our 3 cosine theta. In the denominator, the 3 sine theta squared becomes 9 sine squared theta. Underneath the radical is where this trigonometric substitution becomes important, because we cannot simplify a square root of a polynomial expression. But through some algebra here and a trigonometric substitution, we are able to convert this into a single term. We can start by factoring out 3 squared, which would leave us with 1 minus sine squared theta underneath the radical. And perhaps you can already see where this is going. With the 3 squared factored out, 1 minus sine squared theta is a Pythagorean identity. So that we can replace the multiple term expression 1 minus sine squared theta with the single term expression cosine squared theta. The radical and the squares underneath will then cancel. So we still have our 3 cosine theta in the numerator. We have our 9 sine squared of theta in the denominator. And then the square root cancels with the squares to leave us with 3 cosine theta d theta. Where, of course, now we can simplify the 3 cosine theta in the numerator with the 3 cosine theta in the denominator, leaving us with 1 over 9 sine squared theta d theta. And now we're in much better shape. The 1/9 can be brought out in front as a coefficient, and that leaves us with 1 over sine squared, which is also known as cosecant squared theta d theta. The antiderivative of cosecant squared theta is negative cotangent theta. And of course, we have our ever-present constant of integration once we actually do the integration. Now, like with any substitution, the purpose of it is to convert the integral into the integrand into something that we can more easily integrate. but after we do so, we have to return to the original variable. The triangle that we constructed is useful here again. Recall it is a right triangle with the hypotenuse being length 3, the opposite side being length x, and therefore the adjacent side being length square root of 9 minus x squared. We can then calculate the cotangent of this angle using the expressions for the lengths of the sides of the triangle. Cotangent is adjacent over opposite, which in this case is the square root of 9 minus x squared over x. So our final answer is negative square root of 9 minus x squared over 9x plus c. Which, as always at this point, is not particularly intuitive comparing this to the original function, but if you choose to differentiate it, you can, through some careful algebra, reproduce the original function, or the original integrand. That is the first of our 3 expressions that we can do substitution with. The second is when we have a square root of, well, we're going to go a little out of order and do a square root of a squared plus u squared. Keeping in mind, of course, that this being addition, the terms can be written in either order. In this situation, in order to have a sum of the squared terms, the a and the u must be the 2 legs of the triangle. They can be done in either way, but typically the variable expression is the opposite side, while the constant term is the adjacent side. And thus, by the Pythagorean theorem, the square root of a squared plus u squared is our hypotenuse. This would then allow us to use the relationship that tangent of theta is equal to opposite u over adjacent a. And by multiplying on both sides by a, we have a tangent theta is equal to u, thus giving us a substitution for the variable expression that will remove the original variable and replace it with theta, an expression in terms of theta. For an example of this, let us consider the integral (1 over the square root of 4x squared plus 1 dx. Like in the previous example, it helps to clearly identify our u and our a, in this case, by writing each term in this binomial expression as the square of something. In this case, 4x squared is the square of 2x, and of course 1 is the square of 1. So following the example of the previous slide, we would make 2x the length of the opposite side and 1 the length of the adjacent side, so that the hypotenuse then would be the square root of 4x squared plus 1 by the Pythagorean theorem. So as stated previously, this would give us the ability to write tangent of theta as is equal to 2x over 1. Now we could, in this case, perhaps divide both sides by 2, but since the original expression under the radical actually has a 2x in it, it actually is easier for us to simply leave this as tangent theta is equal to 2x. Therefore, we can directly swap out the 2x for the tangent theta. Like before, we will need to differentiate both sides of this. The derivative of tangent theta is secant squared theta, and the derivative of 2x is, secant theta d theta, and the derivative of 2x is 2 dx. Now there is no factor of 2 in the original integrand, so we will have to divide both sides by 2, thus giving 1/2 secant squared theta d theta is equal to dx. So our integral can now be rewritten in the denominator. Instead of 2x squared, we can replace the 2x with tangent theta squared. The dx can be taken out and replaced with 1/2 secant squared theta d theta. Now it's a matter of cleaning this up. We can bring the 1/2 in front. That gives us secant squared theta in the numerator. In the denominator, we can rewrite this as tangent squared theta plus 1, which, like in the previous example, will allow us to use a Pythagorean identity. Tangent squared theta plus 1 is equal to secant squared theta. So in the numerator, we have secant squared theta, and in the denominator, we have the square root of secant squared theta. The square root of secant squared theta is, of course, just secant theta. The integrand further simplifies to simply secant theta. The lesson on integration by substitution included an example where we established the antiderivative of secant theta through a very particular alteration of the integrand that allowed us to use substitution to integrate it. We may now use that definition freely, and that definition is that the antiderivative of secant theta is the natural log of the absolute value of secant theta plus tangent theta. And of course, the constant of integration at the end. Once again, now that we have finished integrating, we do need to return to the original variable. Once again, the triangle will assist us in this. Our opposite side is length 2x, our adjacent side is length 1, and our hypotenuse is length square root of 4x squared plus 1. So that tangent theta is equal to 2x, as we already know because we used that for our substitution. But we also need secant theta, which is equal to the hypotenuse over the adjacent side, or simply the square root of 4x squared plus 1. Thus, the integral, or the antiderivative, can be rewritten as 1/2 times the natural log of the square root of 4x squared plus 1 plus 2x plus c, which, as always, can be verified through differentiation. which will not be the easiest thing to show, but it can be done if you take the time to do so. The third possibility is that we have the variable term first and the constant term second with a subtraction. The square root of u squared minus a squared. In this case, the convention is to, again, in order to have a subtraction, the first term has to be the length of the hypotenuse. The a can be either side, but by convention it is typically used as the adjacent side, so that the Pythagorean theorem would yield the square root of u squared minus a squared for the opposite side. This would allow us to use the substitution that secant theta is equal to u over a, hypotenuse over adjacent, which can, if need be modified to a secant theta is equal to u. For an example, this time we will use a definite integral. The definite integral from the square root of 3 to 2 of the square root of x squared minus 3 over x dx. In this case, because of the definite integral, we have two options. The typical method that I have shown in previous examples has been to find the antiderivative, and if that process included substitution, we would rewrite the antiderivative in terms of the original variable before applying the fundamental theorem of calculus. There is, however, another option. We can do the substitution and change the variable, and we can also change the limits of integration to fit the new variable. And in that way, we can do the antiderivative, leave it in terms of the new variable, and apply the fundamental theorem of calculus directly. In this case, that is advantageous in many ways because these substitutions are all dependent on a right triangle, meaning that the angle in question has to be between certain a minimum and a maximum value, actually corresponding to the restrictions on the inverse trigonometric functions. When we are using sine or secant, as long as the angle stays between negative pi over 2 and positive pi over 2, we are fine. No special adjustments are needed. But when we are using tangent, we would need to make sure that we are either between 0 and pi over 2, or between pi over 2 and pi. And depending on which section the angle is in, the tangent of theta may actually come out to be negative. Thus, we need to be careful in converting the limits of integration. In this case, because our substitution will be using secant of theta, we should be fine. But we will double check when we use our change our limits of integration just to make sure. Before we get to that, let's proceed as we had previously. We have a square root of x squared minus 3. Which we can describe using a triangle where the hypotenuse is length x and the adjacent side is length square root of 3, so that the opposite side is length square root of x squared minus square root of 3 squared. or simply the square root of x squared minus 3. The relationship between hypotenuse and adjacent is secant of theta is equal to x over the square root of 3, or the square root of 3 times secant theta is equal to x. Differentiating this produces square root of 3 times secant theta times tangent theta, d theta, is equal to dx. This allows us to rewrite the integral. Now, as we are rewriting it into terms of its new variable, we have not yet converted the limits of integration. So I'm going to be very clear and state that these are x values, the limits of integration, because we have not yet converted them. For the numerator, underneath the square root, in place of the x, we can write the square root of 3 times secant theta. I am now going to take this opportunity, as we did in the previous examples, to write the 3 as the square root of 3 squared. We also have an x in the denominator, where we can, again, write the square root of 3 times secant theta in its place. Lastly, our dx swaps out cleanly for the square root of 3 times secant theta times tangent theta d theta. And we immediately get some simplification here. Before we go any further, we can use the relationship the square root of 3 times secant theta equals x, or perhaps better yet, secant theta equals x over square root of 3, to convert our limits of integration. For the lower limit, when x is equal to the square root of 3, secant theta would be equal to the square root of 3 over the square root of 3, or simply 1. The reciprocal of secant theta, cosine theta, would then be equal to the reciprocal of 1, which is 1, and thus theta would be 0. Likewise, we can take the upper limit of integration, x equals 2, so that secant theta is equal to 2 over the square root of 3. The reciprocal of secant theta is cosine theta, and that would be equal to the reciprocal of the other side, meaning that cosine theta is equal to the square root of 3 over 2. Staying within our restrictions, also given that we are dealing with a value that must be larger than the other limit of integration, because 2 is larger than the square root of 3, the theta value that corresponds to 2 must be bigger than the theta value that corresponded to the square root of 3. Thus, the only value of theta that can work here is pi over 6. In this way, we have definitely stayed within the restriction that theta must be between negative pi over 2 and positive pi over 2. So with our simplifications in the integrand and our conversion of the limits of integration to be in terms of the new variable theta, we now have the definite integral from theta equals 0 to theta equals pi over 6. I write the theta equals here to indicate the change in variable. After this, we can simply leave them as 0 and pi over 6. We now have, under the square root of 3 times secant, all squared, can be written as 3 times secant squared of theta minus 3. And outside of the radical, we have tangent theta d theta. Underneath the radical, we can factor out the common 3, leaving us with secant squared theta minus 1, which, through a Pythagorean identity, can be rewritten as tangent squared. Simplifying the integrand then, we can write this as the square root of 3 times tangent theta times the other tangent theta d theta, so that the square root of 3 can be brought out in front as its constant multiple, and the integrand can be written as tangent squared theta. Fortunately, our previous lesson has now enabled us to properly deal with this integral of tangent squared theta, d theta. The rule was that for even powers of tangent, when we are lacking any factors of secant, we can simply use the Pythagorean identity, much as we used earlier to change secant squared theta minus 1 into tangent squared theta. We can now use it in the other direction to rewrite the tangent squared theta as secant squared theta minus 1, which integrates quite cleanly. The antiderivative of secant squared theta is simply tangent theta, where the antiderivative of 1 is simply theta. At this point, because we have converted the limits of integration into theta values, there is no need to return to the original variable x. We can simply evaluate this as written using the theta values we are given. So by the fundamental theorem of calculus, we have the square root of 3 times tangent of pi over 6 minus pi over 6 minus the square root of 3 times the tangent of 0 minus 0. For the first part, we have the square root of 3 times tangent of pi over 6, which is square root of 3 over 3, minus pi over 6. And for the second group, we have the square root of 3 times the tangent of 0, which is 0, minus 0, so that the entire second part of this is equal to 0 and simply cancels out. Now, there isn't much we can do to simplify this, the first part of this, but we can distribute the square root of 3 because it will clean up nicely with the first term. The square root of 3 times the square root of 3 from the numerator actually just gives us 3. So our first term simplifies to 1. Our second term, there isn't much we can do with it, except simply write it as the square root of 3 times pi over 6. This is the exact form of the solution, which is preferable. Being as it is irrational, due to the pi and the square root of 3, it is preferable to leave this in its exact form rather than to give a decimal equivalent. However, if you wish to check this answer using your calculator, you would need to produce the decimal equivalent and then evaluate the integral, the definite integral, using the calculator and show that the two decimal forms of the answers are the same. These are the three different integrand styles that we can use this for. A square root of u squared minus a squared, a square root of a squared minus u squared, and a square root of a squared plus u squared, which again can be written in either order due to the addition. This does extend beyond simply square roots. There are other exponents, rational exponents, that have a denominator of 2, which do qualify for the square root, but more than that, it's about having the two-term expression that is a constant squared minus a variable expression squared, with or without a radical, with or without a rational exponent, of having a variable expression minus a constant expression, both squared, or of having a sum of squares. All we have to do is make sure that those things appear somewhere in our integrand, and then we can apply this method of integration by trigonometric substitution. For example, suppose our integral is of the expression 1 over x squared minus 4x to the 3/2 dx. Now, first of all, this does actually include the square root component because the denominator of the rational exponent is 2. However, you may notice that the expression is not actually a difference of squares. It's an x squared minus 4x. That extra x throws a little bit of a wrench in the works. But there are other algebraic techniques that can help us alter this to get it where we need it to be. Namely, we can complete the square. So the first thing I'm going to do is pull out the expression x squared minus 4x. And this can be written as a difference of squares by completing the square. To create a perfect square trinomial, I would need to add 4 to the existing expression, and to maintain equality, I would then have to balance it by subtracting 4. In this way, the first 3 terms can be written as x minus 2 squared, where the new subtraction of 4 can be written as minus 2 squared, thus producing a variable expression squared minus a constant squared. I am now going to rewrite my integrand as 1 over x minus 2 squared minus 2 squared to the 3/2. And at this point, I am now prepared to construct a right triangle to help determine the appropriate trigonometric substitution to proceed with this. And then later, of course, to use that same triangle to return to our original variable x. By the way the Pythagorean theorem works, the only way to have a subtraction is if the first term of the subtraction produces the length of the hypotenuse. The other term can produce the length of either of the legs, but again, by convention, we typically would, in this case, use the constant as the length of the adjacent side, so that it is the opposite side that by the Pythagorean theorem would be our radical expression. This allows us to then use the relationship that secant theta is equal to x minus 2 over 2, and solving this for x by first multiplying both sides by 2 and then adding 2 to both sides, produces 2 secant theta plus 2 is equal to x. This being said, we can make our lives a little bit easier by simply leaving the subtraction of 2 with the x. Because in our expression, we have the expression x minus 2 already in there. So if we can swap that out more directly in this way, it will make our lives a little bit easier. Part of the reason we like to solve this first equation for x is so that when we differentiate it, we have just dx on the right side. In this case, since the minus 2 is a subtraction of a constant, in differentiating, it will disappear and we will still be left simply with dx. So in this case, it is advantageous to actually leave the subtraction of 2 on the right side. Differentiating this then gives us 2 times secant theta times tangent theta, d theta, is equal to dx. Again, the derivative of the minus 2 is 0, so it is not of any concern here. And now we are prepared to continue to integrate this. We will rewrite our integrand using our new variable, where instead of x minus 2 squared, we will have 2 secant theta squared minus 2 squared raised to the 3/2 power. The dx then will directly swap out for 2 secant theta tangent theta d theta. In the denominator, we can, within the parentheses still, factor out a 2 squared, leaving us with a secant squared theta minus 1, and then that entire expression still raised to the 3/2 power, so that the secant squared theta minus 1, by Pythagorean identity, can be swapped out for tangent squared. So in the numerator, we still have our 2 secant theta tangent theta. And in the denominator now, we have 2 squared times tangent squared raised to the 3/2. Since both of the factors in the denominator are being squared, that will cancel out cleanly with the denominator of 2 in the exponent on the outside, so that we are left with 2 secant theta times tangent theta, and in the denominator we have 2 cubed times tangent cubed theta. And we're going to very nicely get some simplification here. the single factor of tangent in the numerator will cancel with one factor of tangent in the denominator. Likewise, the single factor of 2 in the numerator will cancel with one factor of 2 from the denominator. The remaining two factors of 2 are a constant multiple that can be brought out in front, so that we have in our integrand secant theta in the numerator and tangent squared theta in the denominator. This does not quite fit any of the trigonometric integral styles that we saw in the previous lesson because the tangent of theta factors are in the denominator, and that definitely makes it a little more difficult. The most direct way to handle this actually would simply be to convert the secant theta and the tangent squared theta in the denominator into sines and cosines. To do that, it would perhaps be most helpful to bring the tangent squared up to the numerator, where it will become cotangent squared theta, so that we can write the secant theta as 1 over cosine theta, and the cotangent squared as cosine squared theta over sine squared theta. Thus getting a bit of simplification to reduce us to a single factor of cosine with a power of sine. Even though it's a negative power, having a single factor of cosine means that we can do a substitution with u, or in this case perhaps, well, I suppose we can use u, we haven't used it yet. With u is equal to sine theta. So that du is equal to cosine theta d theta. And our integrand now becomes simply u to the negative 2. The power rule will work nicely here. This becomes u to the negative 1 over negative 1. And now we actually have two levels of substitution to back up through. We have to return from u to the variable theta, and then return from theta back to the original variable x. So handling this one step at a time. The division by negative 1 can simply, times the 1/4, can simply be written as negative 1/4. And then we have sine of theta to the negative first. Please note this is different than sine to the negative first, which would be inverse sine. So that this can now be written as negative 1/4 times cosecant theta. Returning now to our triangle from a couple of pages back. Remember the hypotenuse was length x minus 2. The adjacent side was length 2. And the opposite side was length x minus 2 squared minus 2 squared, which was a form that we created in order to make this a difference of squares. The original form of this was simply the square root of x squared minus 4x, which admittedly would probably be nicer for writing our answer. Cosecant of theta then would be the length of the hypotenuse over the length of the opposite side. Thus giving us a result of negative x minus 2 over 4 times the square root of x squared minus 4x plus c. A long problem to be certain, but the important thing is that we can get there. So again, if we have an expression that is not quite a difference of squares, but we can complete the square, then we can still apply these techniques. The next question, and final question of this lesson, is how relevant is the square root? That is to say, can we do an expression that simply contains an a squared minus u squared without the square root? Or a u squared minus a squared? Or an a squared plus u squared? Is the square root necessary for each of these? And the answer is no, not strictly. Consider a more basic rational function as our integrand that does contain a binomial that is a sum of squares. The fact that it has a sum of squares is enough to make this work. The lack of a square root is actually not immediately relevant. We can still use the idea that if it is a sum of squares, it means that the x being squared in the first term and the 1 being squared in the second term would have to be the legs of the triangle. Again, by convention, the variable expression is used for the length of the opposite side in this case, where the constant is used for the length of the adjacent side. By the Pythagorean theorem, then, the length of the hypotenuse would be the square root of x squared plus 1. This is fine so far, because remember that x squared plus 1 is simply the square root of x squared plus 1 squared. So when we are ready to do our substitution, we can handle it thusly. For a conversion to the variable theta, we would use the relationship that the tangent of theta is equal to x over 1, or simply tangent of theta is equal to x. Differentiating gives us secant squared theta d theta is equal to dx. And now we are prepared to do our substitutions appropriately. X is equal to tangent theta. So x squared is tangent squared theta. Dx then cleanly swaps out for secant squared theta d theta. The rest of this is going to clean up surprisingly well. Through the Pythagorean identity, inside the parentheses in the denominator, tangent squared theta is substituted with secant squared theta. So that the denominator becomes secant to the fourth of theta. And of course, then, with powers of secant in the numerator and powers of secant in the denominator, we get some very obvious and simple simplification. So that we are left with 1 over secant squared theta. This is perhaps most easily rewritten as simply cosine squared of theta. Reaching back to our lesson on trigonometric integration, we have an identity that would suit us well here. Cosine squared of theta is equal to 1 plus cosine of 2 theta all over 2. To save us a little time, I will bring the denominator of 2 out in front as the coefficient of 1/2, so that our integrand will become 1 plus cosine of 2 theta d theta, which certainly is easy enough to integrate. We have our 1/2 in front. The antiderivative of 1 is the variable theta. And because the inside function of cosine 2 theta is linear, it might be very easy to do this substitution without having to go write out all of the steps of it. But if you feel the need to, you certainly can. We can use the substitution here, u equals 2 theta, so that 1/2 du would be equal to d theta. And I'm going to omit some of the steps here. This will then become 1/2 sine of 2 theta. Now, the problem here in going back to the original variable is we can't do it just yet. We certainly can find an expression here to give theta in terms of x, but the problem is we can only work with theta, not with 2 theta. I mean, if it was simply 2 theta, it would be fine, but we have no idea. We don't have a triangle that describes the sine of 2 theta. We only have one that would give us sine of theta itself. So we are going to have to use another identity here. We're going to have to use the sum formula, the sum identity for sine, or rather the double angle formula might be more appropriate here. Namely, that the sine of a double angle, such as 2 theta, would be equal to 2 times sine of the base angle theta times cosine of theta. Which takes care of the coefficients, but it also gives us sine of the angle theta and cosine of the angle theta, both of which can easily be determined using the triangle that we constructed. So we're calling that triangle. We had an opposite side length x and an adjacent side length 1, and a hypotenuse length square root of x squared plus 1. So that from this triangle, sine of theta is equal to x over the square root of x squared plus 1. And cosine theta is equal to 1 over the square root of x squared plus 1. That gives us the two components that we need to fill in this, or two of the components we need to convert this back into the original variable x. The other we're missing is the value of theta itself, which we do already have the previously established relationship that tangent of theta is equal to x. This was the substitution we used originally. This can easily be solved for theta by using the arctangent. And this is why these trigonometric substitutions have a limitation on them, because in order for the relationship tangent theta equals x to work, we need to be able to define theta in terms of x, and that requires the inverse functions. and those inverse functions have restrictions on them. So, given these three equivalencies now, we have a 1/2 times theta, which we now know to be the arctangent of x, plus the sine of theta x over the square root of x squared plus 1 times cosine of theta 1 over the square root of x squared plus 1 plus c. We can simplify that multiplication because they have the same denominator. We end up with the square root of x squared plus 1 squared, so that the radical simply disappears from it. So that we have x over x squared plus 1. The 1/2 can then be distributed, but at this point we're talking about a matter of semantics. Now, there is one remaining question. Every time we've constructed these triangles, I've said that we can assign values to the legs, the lengths of the legs, in more than one way, but there is a convention to always do it a particular way. And if you've noticed, it always results in the trigonometric function of sine, but not cosine, tangent, but not cotangent, and secant, but not cosecant. It's not that the co-functions are not usable, but since we have to differentiate whatever trigonometric substitution we're using, the co-functions, when differentiated, always produce a negative. The derivative of cosine is negative sine, for example. The derivative of cotangent is negative cosecant squared. Thus, the other three, the sine, tangent, and secant functions, are preferable to use because they do not produce that negative sign in the differentiation. And it just makes our lives a little bit easier to do so. If you choose to, it is possible to set up these triangles to use the co-functions, but they are typically set up to use the non-co-functions, the sine, tangent, and secant, to avoid that negative in the differentiation, to avoid that extra complication in the algebra of our substitution and simplifying the new form of the integrand. So if you choose to do them the other way, you can attempt to do so, but by convention, it is done with sine, tangent, or secant.